Hey everybody, I'm going to run through the this year video answer key for the Unit 6 Lessons 4 through 5 practice. I'm going to run through each of those problems, talk through my thought process. Please don't watch this entire video. Skip around and look at the ones you need to look at. And the other thing I did want to give you a heads up on, I wanted to talk about the chart that I gave you because I did correct one part because I don't know what I was doing on Sunday night when I was typing this, but apparently my brain turned off for half a second. We have one change that I made. So on yours, it said the samples are independent. All right, and I just had a moment. We're going to get into this in a little more detail in the next chapters, but I wanted to go ahead and put this in here because one of the conditions, we've only done 10% conditions so far as a way to check for our for standard deviation. There is another loophole. And again, we'll get into this in the next unit, but I wanted to go ahead and put it on this chart so you had it because you're going to be referring back to this chart in the next units because we use these same formulas. So what we're getting at there is for the standard deviation, you've got two options. One is 10% condition. Your sample is is smaller than 10% of your population. If you have that, you can use that standard deviation formula. The other condition, and this is again where I need you to change it on your paper, is the samples are taken with replacement. So what that would mean is if I took a sample and say, let's go back to that Reese's Pieces example that we used the whole first week with this. All right, so I have a couple Reese's Pieces and I'm going to take a sample, and my sample is going to be 5 of those Reese's Pieces. I would take out one, record the information about it, put it back in the cup, shake it up, and then pull out another one. That's taking a sample with replacement. So you're putting it back in before you draw your second one. And we dealt with that a little bit in probability. We dealt with that actually in our very first unit when we were talking about designing our experiments. So heads up that that's a thing. We will be, like I said, using this in the further units, the next two. So I wanted to go ahead and put it in there. But for right now, all we're really worried about is 10% condition. But I did want you to go ahead and make that change on the chart so you have it moving forward. For all of your homework problems, none of them were samples were taken with replacement. They're all 10% condition. So don't let that throw you off. All right, so there's your chart. Hold on to it, save it. If you have not downloaded it yet, I am going to upload the updated corrected version as soon as I'm done making this video. So if you download this after probably 12:30 on Tuesday, you're fine. You have the updated version. If you have the paper copy or you downloaded it prior to that, you may want to go back and get the new one or just hand correct it on yours. Either way. All right, so let's talk through these 6 questions. So these are a mix of 1 sample and 2 sample means problems, all right, for our sampling distributions. So what I'm going to do is just walk through them, talk about my thought process. I have posted the answer key on Canvas already, so if you have that and you want to follow along, it's slightly different, because my sentences always come out slightly different every time I do it, but you'll have them there as a reference. All right, so for the first one, we have a school is dealing with a distribution of backpack weight. So we say the distribution of backpack weight is approximately normal with a mean of 10.7 pounds and a standard deviation of 3.1. A random sample of 5 backpacks will be selected and the weight in pounds of each backpack will be recorded. What's the probability that the average backpack weight from the sample is greater than 22 pounds? All right, so there are 3 things you have to do before you can do your probability. First, you have to establish that it's going to be normal. You have to find your mean. You have to find your standard deviation. Those are the 3 things you have to do. So for this first one, there are 2 options when we are dealing with sample means to figure out whether something is approximately normal. Either the original population is normal or approximately normal, and they tell you that, or you know that your sample size is large enough, it's larger than 30, and so the central limit theorem tells us if our samples are 30 or larger, we have enough and we can assume our sampling distribution is approximately normal. In this case, they come out and tell us the population is approximately normal. So I think it's a good practice to at least write a sentence. I'm not saying the full descriptive one, but you at least want to establish why you are using a normality. You're assuming normality. So in this case, I would say the sampling distribution of X bar is approximately normal because the population is approximately normal. And for homework, feel free to abbreviate as needed. On the AP exam and on my tests and quizzes, make sure you write it all the way out. But for now, abbreviating is fine for the homework. All right, so let's talk through our mean and standard deviation calculations. So the mean's super easy. It is exactly the same as the population mean. And if you forget that, it is on your formula sheet that you get on the AP exam, as well as the one that, the chart that I gave you that we just talked about. I do want you to start getting in the habit of using units because context and units are important. All right, so our average backpack weight at this school is 10.7 pounds. And so for our sample, we would expect our average backpack weight to be the same. All right, now standard deviation. So your formula for standard deviation is the standard deviation of the population divided by the square root of your sample size. So our standard deviation was 3.1. Our sample size was 5. So that's the fraction that we're going to have to calculate. So when we work that out, you end up getting 1.39 pounds for our weight. All right, now what you need to watch out for here is, again, proving either 10% condition or in the next unit using sampled with replacement, that you can go ahead and use this formula. So in this case, 10% condition would mean at this high school, there has to be at least 50 backpacks. I don't think that's a stretch. I think we're good to go there. So we can go ahead and assume that we can use this formula. So there are more than 50 backpacks. And again, that's coming from the 10% rule, which means that your sample size has to be smaller than 1/10 of your population size. So if you have both numbers, you can just plug it into the formula and look. Most of the time you don't. So when you don't, all you do is you take your sample and multiply it by 10 and see if that's a reasonable assumption that your population would be bigger than that number. In this case, our sample was 5. Multiply that by 10, I get 50. It absolutely makes sense that there would be more than 50 backpacks at a high school. So that works and we can move forward. All right, now what they're asking us to find, they say, what's the probability that the average backpack weight from the sample is greater than 22 pounds? So I have been starting this on the homework just to keep you guys a little organized and for you to see what my thoughts are. It's not a bad practice to get into, to write out what you're finding before you jump in and do it. So in this case, what we're looking for is we are looking for if the probability that our sample, our 5 backpacks, has an average higher than 22 pounds. Now let's stop and think about that for a second. The average at the school is 10 pounds. 22 pounds is a lot bigger. All right, so I would think that that probability is probably going to be pretty small. Like, think about that. A 22-pound backpack, that's a lot of stuff. And for that to be the average, and you found 5 people that all have super heavy backpacks, that's, I mean, it's possible, but it's not super likely. So let's see what we end up getting for our probabilities. All right, so our first step is to draw our picture. All right, our mean was 10.7. we need to label it. So N 10.7 and then our standard deviation, which was 1.39. All right, we are looking for 22. So that is way the heck over here on the number line, and we wanted it to be greater than 22 pounds. So we're shading this way. All right, so first, after we draw our picture, our next step is to do our z-score calculation. So it's our value of interest minus our mean over our standard deviation. Well, when you mash your buttons in your calculator, you are going to end up getting 8.13 as a z-score. That is super big. All right, when we get to what we're talking about in our next units, that should be a red flag for you. But for right now, let's talk through hypothetically what that would be. All right, so our z-score is 8.13. So if I go to my reference table, drag that over here, sorry. All right, for my reference table, if I try to go to 8.13, my reference table only goes to 3.49. All right, so we are not going to be able to get an exact answer, and that's okay. So if we go to 3.49, we get 0.9998. All right, so table A would give us something larger than 0.9998. Oops, left out a word. All right, now we're doing greater than. So we would have to subtract that. And we would get 0.0002. But we know it has to be smaller than that. So we won't be able to get an exact answer. But what we can do is write what we know. So we know that the probability that x bar is greater than 22 is less than 0.0002, which is extremely unlikely. So the probability that we're going to get a sample of 5 backpacks that has an average weight of 22 is really, 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 really low. All right, real quick reminder. So table A, we said we knew it had to be larger than 0.9998. And then I subtracted because what we were looking for is the greater than side, as we shaded to the right. So I have to do 1 minus. And so when I'm subtracting that, that's then when it switched from larger than to smaller than, all right, or less than. So that's what's going on there. All right, so that's number 1. And you can't get an exact answer there, and that's okay. That will happen. And we haven't run into it much yet, but in stats, that does happen. And we just roll with it. All right, so that is the first one. All right, next up, let me slide my screen back over there. All right, so we have dental disease in domestic cats. All right, so number 2 and number 3 were actually questions on last year's exams. These were some of the released ones that they put out. Dental disease in domestic cats is commonly associated with the accumulation of plaque on the teeth. A cat food manufacturer is studying the accumulation of plaque on the teeth of cats from certain population. The accumulation of plaque is assessed using a fluorescent light technique, where an evaluator reviews images of the cat's teeth and assigns an overall rating from 0 to 10, with lower values indicating less plaque. All right, so they just gave you a whole bunch of information that you really don't care about. All we really need are the numbers. It says a previous study indicates the population distribution of the FLT ratings for teeth of cats is bimodal, with a mean of 6.3 and a standard deviation of 2.2. All right, describe the sampling distribution of the sample mean rating X bar for random samples of 400 cats from the population. All right, so if we're going to describe the sampling distribution, this is where we write the fancy sentence, but we have to find all our things first. All right, so we do know that the sampling distribution is going to be approximately normal. Now, they don't tell us that the population is normal. In fact, they say it's bimodal. But what makes it approximately normal is because our sample size is larger than 30. Our sample size is 400. And that's the central limit theorem. So our sampling distribution is approximately normal because 400 is bigger than 30. And that's our central limit theorem. All right, then we also need the mean to be able to do a description. So the mean of X bar is the same as the mean of the population. So that should be 6.3. And then standard deviation for X bar is standard deviation of the population divided by the square root of the sample size. So we have 2.2 over the square root of 400. And when you mash your buttons on that, you're going to end up getting 0.11. All right, so we have 400 as our sample size. Multiplying that times 10 would give us 4,000. There are more than 4,000 cats in the general population, so we would be good to go. The heck? There we go. The thing decided it needed to jump. All right, so we haven't, God bless, sorry y'all. We haven't actually answered the question yet. So the question was, describe the distribution. And so this is where we have to write the fancy sentence, and we need to include context, and we need to include our units. So we have to be careful with that to make sure we're ticking all those boxes for what they're looking for. All right, so to describe this, and I forgot this is part A. All right, so the sampling distribution, and I am taking the context straight out of the problem. So the sampling distribution of the sample mean FLT rating, which is X bar, is approximately normal with a mean of 6.3 and a standard deviation of 0.11. Now, a minute ago, I said we needed to include units. However, do we have units in this problem? We don't, because it's just a rating. There's no units. I mean, I guess you could put like points on the end if you really were like stretching to come up with one, but in this case, there's not any. So if there are units, use them. If there are not, don't worry about it. All right, so that was part A. Part B asks us to do a probability calculation. It says calculate and interpret. So for my folks that were asking about that, this is how you know. Calculate and interpret the value of the probability of X bar being less than 6.41. All right, so that's what we're going to find. So we have our mean and our standard deviation. So now it's just jump straight into drawing the picture. All right, so the mean was 6.3. Our label, 6.3. And our standard deviation was 0.11. All right, what we're finding is when X is less than 6.41. So less than, we shade to the left. All right, so that's what we're looking for there. Remember, that's half credit on these probabilities, just drawing the picture. So when in doubt, draw the picture. All right, now next part, we need to do our z-score. So it's going to be 6.41 minus 6.3 over our standard deviation. That is going to give us positive 1 as our z-score. And when you go to table A, a z-score of 1 is going to give you 0.8413. So our probability statement would be the probability of x bar is less than 6.41 equals 0.8413. All right, so now we found it. We've done the calculation. Now we have to interpret it. So we're still using what we talked about before. And we're just going into describing everything that we've used that's gone into this. So the probability that the sample mean of the FLT rating x bar of a sample of 400 cats was less than 6.41 is 0.8413. So you're just basically putting all of the information you know into that sentence. I don't know if y'all can hear that on the mic, but the wind is whipping outside today. All right, so thank you for bearing with me. It takes a little while to write out. So you have to include the context, you have to include your sample size, and you have to say what you're finding the probability of. So we are finding the probability that x bar was less than 6.41, and then actually say the probability. So that's what your interpret needs to look like. All right, so number 3 is basically the same problem, just going through with different numbers. We are going to run into the same issue we ran into with number 1, though. So let's go ahead and take a look at that one. It says the common house finch is a small songbird that begins to look for a mate in early winter. An ecologist plans to investigate the number of mating calls per minute for the finch during mating season. A previous report suggests the population distribution of the number of mating calls per minute for the finch is skewed to the right, with a mean of 6.5 and a standard deviation of 1.6. So we're going to describe the sampling distribution for a sample of 6,464 finches, and then we're going to calculate and interpret a probability. All right, so first off, we need to say that this is normal, and it's normal because of the central limit theorem. The sample is 6,464. That is way larger than 30, so we're good to go. That's the central limit theorem is where that comes from. All right, next up is our mean. So the mean of x bar is the same as the mean of the population, which was 6.5. Standard deviation mean, it's the standard deviation of the sampling mean. There we go. The standard deviation of the population was 1.6, and we're going to divide it by the square root of our sample size. All right, and when we do that, we are going to end up with, oh, that's what happened. All right, so I'm going to adjust this just a little bit. So this is going to be different than what's on your answer key. I think I typoed, and that wasn't supposed to be 6464. I think it was just supposed to be 64. And that's why it wasn't working out otherwise. I think I typoed that. So we're going to adjust this on the fly and assumed instead of 6,464 finches, I meant 64 finches. If you did it the other way, that is totally fine. Don't change your answer. But I do want to show you the calculations all the way through. All right, so when we work it that way, should be 1.6 divided by 8, which is going to give us a value of 0.2 for our standard deviation. All right, 10% condition, if there's 64 was our sample, if that's what we're assuming, then the population would have to be larger than 640. And that makes sense. There would be more than 640 finches in the world. All right, so now we have to actually write our description. So this is the fancy sentence. The sampling distribution of the sample mean number of mating calls per minute X bar is approximately normal with a mean of 6.5 calls and a standard distribution, or I'm sorry, standard deviation of 0.2. All right, so that's part A. Part B is asking us to go through and do the calculation. All right, so we are going to find the probability that X bar is greater than 6.1. That's what we're looking for. So first up, draw the picture. So 6.5 is our mean. Put in our label. All right, we're finding the probability that the mean is larger than 6.1. So we're shading to the right. So we're going to do our z-score. So it's 6.1 minus 6.5 over 0.2. And that is going to give us -2. So then we're going to go to table A and find the z-score for -2. And that ends up being 0.228. Now, we shaded to the right. What we just found in table A is to the left. So we have to subtract from 1. And when we do that, we're going to get 0.9772. All right, so that's our probability. The probability that X bar is greater than 6.1 equals 0.9772. All right, so let's stop and talk about that for a second. That's a really high probability. So it is very likely that that you would get a sample that had an average of 6.1 or higher for the number of calls per minute. All right, so we need to write this sentence to interpret it. So the probability that the sample mean number of calls, of mating calls per minute for a sample of 64 birds is larger than 6.1 calls per minute. Remember, we want to use our units. is 0.9772. All right, so when you're writing your sentence, you want to make sure you're using context. You want to make sure you're getting in your sample size. You want to make sure you're saying what your unit or your number of value was, or your value of interest, sorry, not number of value. That doesn't make any sense. Your value of interest, which is 6.1, and then what the actual final probability was. So make sure you're including all of that in your answer. All right, so we've done 3 examples of 1 sample. So now we're going to transition and start talking about 2 samples. There are a lot less of these sampling distributions out there. Generally, previously, before they changed the course and exam description, the CED, they would just skip straight over this and go to the 2 sample tests. But now they're including it to kind of solidify your knowledge beforehand, which I think is really good, but that also means that they don't test for it very often. You'll get tested on this in the bigger confidence interval and significant tests that we're going to talk about next. So this is something that helps you with those, but is not necessarily something you're going to see on the AP exam. All right, so number 4, a large school district held a district-wide track meet for all high school students. For the 2-mile run, the population of female students participating had a mean running time of 8.8 minutes with a standard deviation of 3.3 minutes. The population of male students participating had a mean running time of 7.3 minutes with a standard deviation of 2.9 minutes. Suppose 8 female students and 8 male students who participated in the 2-mile run are selected at random from each population. Let X bar F represent the sample mean running time for the female students, and let X bar M represent the sample mean running time for the male students. What is the probability that X bar F minus X bar M is less than 1 minute? All right, so we still have to do all the things. We just don't have to interpret either one. We don't have to describe it, and then we don't have to interpret our answer. All right, so first thing we have to establish is, can this be normal? And what we've got to do here is take a look at, remember our 2 options. Either we have our sample size is large enough, it's greater than 30, or they tell us that the original populations are normal. Well, neither one of those are true. They don't tell us that our populations are normal, and they don't tell us that the sample sizes are larger than 30. In fact, each of them are 8, so that's less than 30. So the reason why I picked this question is because I wanted you to see how you would write this if you ran into this situation. So we're going to say that we know that we can't prove that this is approximately normal, but we're going to proceed with caution. So if both original populations are approximately normal, then X bar F minus X bar M will be approximately normal. However, this is not stated, so we will proceed with caution. And stats is kind of fuzzy like that. They will let you, and this is what happens with real statisticians too, is they kind of fudge stuff a little bit. They come out and say why, like we have these rules, and I know that my data doesn't meet those rules. I'm going to do it anyway, but I'm at least acknowledging that this isn't true. And part of that comes from the fact that all of this is arbitrary. Like the central limit theorem, somebody picked 30. It's not like it's a mathematical law. Same with the 10% condition. Somebody picked 10%. It's not like it's a law. So this is what we use, but it's not hard and fast, so you can work around it a little bit. So when I say proceed with caution, what we're getting at there, and this is also, again, what statisticians would do, is you're indicating to your audience that, hey, like I know this doesn't work, but I'm going to go ahead and crunch the numbers anyway, but you want to take my answer with a grain of salt. Okay, so that's what that's getting at there. All right, so as long as you acknowledge that, then you can move on with your life and keep going with the problem. All right, so we need to find the mean. So the mean of x bar f minus x bar m. All right, so x bar f, the mean of that one is 8.8. The mean of x bar m is 7.3. When I subtract those, I'm going to get 1.5. And my units for that would be minutes, because we're talking about 2-mile times. As an aside, speaking as a former track coach, these kids are all heading to the Olympics if that's what their 2-mile time is. I'm just saying. If that's what their average 2-mile time is. There we go. Okay, now standard deviation. So this is based off of the formula we were using for the first 3 problems, but remember we can't add standard deviations together. We have to add the variances together. So that's why this formula looks a little different. So it's the standard deviation of XF squared. So the standard deviation for the female runners was 3.3. So it's going to be 3.3 squared divided by the sample size, which is 8. And then it's the standard deviation for the men, which was 2.9. And we're going to square that. And it's over the sample size, which is also 8. All right, so when we crunch our numbers on that one, we're going to end up getting 1.55. You could go add another decimal place if you want. There's no hard and fast rules. It's not like calculus where you have to go to 3 decimal places. You do you. All right, so we have those. 10% condition. This tells us that the track meet is for all high school students in the district. So in that case, that it's not unreasonable to assume that there might be 80 female students and 80 male students that are competing. So that seems feasible. All right, so from here, we're going to go through and just actually do our calculation. What we're looking for is we want to find the probability that x bar f minus x bar m is less than 1 minute. All right, so that's what we're aiming for with our calculations. So first we draw our picture. Our mean is 1.5. Our standard deviation is also 1.5. It's just got some extra decimal points hanging out. And we're looking for less than 1. All right, so now we need to switch gears and do our z-score. So we're going to have 1 minus 1.5 over 1.553. And when we work that out, we get a z-score of negative 0.32. So when I go to table A and look that up, it's going to give me a value of 0.3745. Now I need to stop and check. Do I need to subtract from 1? No, I don't. I'm good there. So I just need to write my probability statement. So the probability that x bar f minus x bar m is less than 1 equals 0.3745. This one didn't ask me to interpret, so we're good. Just stop there. All right. Question 5, talking about chickens. All right, so we have a population of Leghorn chickens and a population of Sussex chickens. They give us a table that has all of the information we need. Both of them have a sample size of 36, and then we have our means and our standard deviations. So the actual question says, Mike claims that for all samples of size 36 from the population of Leghorn chickens and all samples of size 36 from the population of Sussex chickens, the mean of all the possible differences in sample means, Leghorn minus Sussex, is 0.3 eggs per chicken. Is Mike's claim correct? All right, so for this problem, all they're asking us about is the mean. We're not finding a probability. We're not finding a standard deviation. We don't even need to say it's approximately normal. All we care about is the mean. Now they tell us specifically what order to go in. They want Leghorn minus Sussex. So if for this one, since they don't establish the subscripts, as long as that makes sense, you can use whatever. So L and S makes sense. You're good there. If you use something other than L and S, you're going to want to explain off to the side. So if you did 1 and 2, say 1 equals Leghorn, 2 equals Sussex. Or if you did X and Y, same thing, just label it. But if it's obvious, you're okay. All right, so to do this, we would do the mean of the Leghorn minus the mean of the Sussex. So mean of the Leghorn is 0.75. Mean of the Sussex is 0.45. When I subtract those, I get 0.3. Yes, Mike is right. All right, so this was a multiple choice question that I just cut the multiple choice off of. So that's to give you an idea of a type of question that you might see on the AP exam that deals with this. It would be quick. It's something like this where it's super obvious when you look at the table. It doesn't require a lot of calculations. And that's generally indicative of what your multiple choice are going to look like. It's much more of, can you write the formula? Did you fill things in correctly? Can you observe a real short mental math type one? The FRQ is where you really have to dig in. All right, now the last one, distribution of ocean wave height. All right, so I'm gonna go ahead and basically stop here because I forgot to put standard deviations in the problem. And without standard deviations, we can't do anything. What we can say is we can say that this would be approximately normal because they tell us both populations are approximately normal. We could figure out the mean. We know that much. When we subtract that out, you would get a mean of 0.6 feet from your waves, but we can't do anything else without the standard deviations. So we will stop there. You guys got off a little easy on that one. All right, so this is it. Hopefully this was helpful for you, and I will see you guys in class on Thursday. If you have questions, shoot me an email.